In this video, we look at a question on dimensional analysis, which is of two parts. First, we ask to determine the dimensions of G, which is the universal gravitational constant. And secondly, we are asked to establish whether this expression over here, given by V is equal to root of 2gm over r, is dimensionally correct. The theoretical basis of this question is Newton's law of universal gravitation, which makes us to believe that there exists a gravitational attraction between all objects having masses, so that given two objects with masses m1 and m2, there would exist a force of attraction between them. That is to say, the object with mass m1 would attract the object with mass m2, and vice versa, the object with mass m2 would attract the object with mass m1. And the greater the mass of the object, the greater its force of attraction on the other. And it is the existence of this force that causes objects to fall towards the Earth under gravitational pull. Of course, this law also applies to interaction of celestial bodies like the Earth orbiting the Sun and of the Moon orbiting the Earth, which will mean that there's going to be a force of attraction of the Earth on the Moon, and equally a force of attraction of the Moon on the Earth, generating a gravitational dynamic between the two celestial bodies given by this formula. But in this question, our focus is very simple. We are asked to determine the dimensions of G. So let's go ahead with the solution. Now we have been given the formula where G is the gravitational constant, M1 and M2 are the masses of the objects involved, and R is the distance between the two objects with masses M1 and M2. But we are asked to find the dimensions of G, so G will be given by So in order to determine the dimensions of G, let's go ahead and determine the dimensions of the quantities force, distance, and the product of M1 and M2. Now, according to Newton's second law of motion, F is equal to ma, where m is the mass of the object and a is its acceleration. The unit of mass is kilograms, and the unit of acceleration is meters per second squared. So the dimensions of force is given by that is the dimensions of mass, and the dimensions of acceleration keeping the dimensions in their MLT format. So we have the dimensions of force as the dimensions of distance is given by, but in the expression we would need for the dimensions of r squared, which is going to be and the dimensions of the product of m1 and m2, the units of mass. So the dimensions of the product of m1 and m2 is going to be so the dimensions of m1, m2, we're going to have now with these dimensions, we're now going to plug them into this expression to determine the dimensions of the gravitational constant. I mean the universal gravitational constant. The dimensions of force is given over here, so we just plug them in. Dimensions of distance squared is going to be this. And the dimensions of M1, M2 is given over here. So in simplifying, applying the laws of indices, we're going to have as our numerator and our denominator so finally we're going to have so this is the dimensions of the universal gravitational constant. And that is the first part of the question. Now we go to the second part of the question, which is given by which is the escape velocity. And we are expected to establish that this expression is dimensionally correct. So we will go ahead and determine the dimensions of the quantities given in the expression and plug them. Now, velocity, we're going to find the dimensions of velocity. The dimensions of the universal gravitational constant has been determined as this: the dimensions of mass and the dimensions of distance. Now, the units of velocity is meters per second. And so the dimensions of velocity is going to be so that is the dimensions of velocity. So we're going to plug in the dimensions into this expression over here. The dimensions of velocity, which is on the left side, is given by dimensions of universal gravitational constant dimensions of mass dimensions of distance. So we go ahead and simplify. So here we consider the rule of indices, consider the base dimensions and add their exponents. And so the base dimension of mass, so we add -1 and 1, and we get the base dimension of length and the base dimension of time. So we simplify further. Further simplification. So let's go ahead and apply this exponent half here to all the exponents within this square bracket. And we are going to have So at this point, we can now conclude by comparing the left side, the dimensions of the left side of this equation to the right side of the equation. At this point, dimensionless constant and dimensionless quantities are not taken into account. And so the dimensions of the left side of the equation equals the dimension of the right side of the equation. We can now conclude by saying that the expression V is equal to is dimensionally consistent. So this is the end of my video. Thank you very much for watching, but keep watching.